So I want to start answering today the idea mentioned at the end of class Monday. What do I do if I've got two different populations?
Is this starting for next, like the next test or the test?
This is chapter 10. This is still on this coming out test. Right, it'll be 8, 9, and 10. How do I deal with two samples? There are a couple of distinct advantages here. I can use everything I already know about one sample test. Rather than compare to a benchmark, I'm comparing my two sets with each other's. So before and after a change in manufacturing, old version versus new version, an experimental group versus a control group. 99% of real experimental data is gathered in exactly this way. I might not know the value I'm looking for. That's what our benchmark was. As I was talking about the call center, we said we wanted at least half of the calls to be answered finished in under 2 minutes. Well, I may not know what the actual numerical value should be, but I say, is there an improvement? Is there a difference? I'm going to have to go through the same procedures. I'm going to have to find a null hypothesis and an alternate hypothesis. I'm going to have to do some sort of test statistic, and then from that, find a critical value or an answer that I can use to justify whether to accept or reject that null hypothesis. By default, the null hypothesis should be everything's okay. But if I'm comparing two groups to each other, that should mean there's no real difference. Again, tying this to the word null, there's no real difference. Whether I'm dealing with means or proportions doesn't matter, but the groups are effectively the same. Why is this my default null hypothesis?
Yeah, it's like a likely outcome you're maybe to expect, maybe like the baseline, that kind of thing.
Yes, I'm hoping that's the baseline. But there should be some variation in my parameter anyway, right? I'm sorry, in my statistic. The parameter for the group exists. I don't know what it is. I'm average, right? So let's think about this as an average. I take group one, I give them a thing I want to measure. Here's a test. What's the average? I take group two, I give them the test. What's the average? There should be some variation there automatically, right? I don't expect group one's average was 72.6. I don't expect group two's average to be exactly 72.6. There's some level of sampling variation that's going to happen. So they might be different, but it might just be random chance. Is it different enough to matter? This is why default is that they should be on silent debug. Because of sampling variation, I need to do that test statistic calculation. Even when I get two samples from the same population. I could take 5 of you and ask how many hours did you sleep last night? And get an average. I could then shuffle the names and draw 5 again and ask how many hours of sleep did you get last night. I might pick the same person twice, right? I might not. I might get 5, but would you expect there to be different estimates from those two groups of 5? As opposed to me taking all 20 of us and saying, how many hours of sleep did we get last night? That would be the parameter. I had 2 different shots at. Now, I could then ask the question, what caused the difference between the groups? I don't know. I have no idea about cause here, just about the comparison between the two groups. There again are 3 different varieties here of a null hypothesis, depending on what I mean by no difference. But the process is going to be the same. I'll have a null hypothesis, I'll have an alternate hypothesis. I'll have a decision rule. I'll have a test statistic and a critical value and a p-value, and then I'll be able to decide. Let's think about means, because that's where we spent a lot of time. We'll do proportions as well, but we'll start with means. So I have my 2 groups, group 1 and group 2. And I have these 2 means. Now, I was listening to the radio this morning, and they were talking about tax returns, because today is tax day. I hope you all got your taxes in. There was a commercial for one of the tax services, H&R Block, Jackson Hewitt, I don't remember which one. And they said, we guarantee a $300 improvement in your return, or your filing fee is waived. That's a difference in average return, right? I want to say I took all of these returns that didn't use Jackson Hewitt or whatever tax service it was. I took these returns. These have a $300 improvement. Well, that's the average of group 1 versus the average group 2. But instead of thinking about comparing them directly with each other, think about a difference between them. So let's let D0, D for difference, is the hypothesized difference between my means. In a lot of cases, I actually set this difference to be 0, and I'm just asking, are these different at all? But in the example I just gave you, I said $300. There's a particular value. I could say people who used this weight loss medication lost weight in 3 fewer weeks, or took off 5 more pounds, right? There's some difference involved. People who studied using this textbook earned at least 10 more points on the GMAC exam, or whatever it is. I could have a null hypothesis that says the difference between my two means is exactly that number. I left space on purpose. I just said, though, a couple of these were at least, right? So maybe I could say that the difference is at least D0. Or I could say that the difference is less than or equal to this number. So I have three different versions of a null hypothesis. This should look awfully familiar, because those are the same three ideas that we did with a benchmark. We had our average is less than or equal to some number, bigger than or equal to some number, or equal to that number. In this case, I'm not just looking at one mean, I'm looking at the difference between the two. For each of these, I should have an alternate hypothesis. What does my alternate hypothesis look like in that middle case?
If he does not equal.
Exactly. And in the case over here on the first one,
Would be less than.
and over here, it'd be greater than. Notice which group you call group 1 and which group you call group 2 matters in these outside two. Doesn't matter in the middle one. I don't care which one is group 1 and which one is group 2. In this case, I just want to know if they differ. My alternate hypothesis tells me about the way I'm going to make my decisions. This is asking, are we to the left of our number? This is a left tail test. This is asking, are we to the right of our number? This is a right tail test. And this one is a two tail. So I'm going to need to compute some sort of a test statistic based on the two samples I got. So I go out and I do samples now. And I get samples. I get an average for each one. Those are the two different parameters I'm comparing, right? What I could do is I could just subtract them in advance, do x1 minus x2, and then I have a benchmark, don't I? X1 minus x2 versus D0. What I've done is I've taken two samples and rewritten them so that I have basically one sample. The sample now is the differences between pieces. Okay. I am making an assumption here. I am assuming that the sample 1 group is completely independent of the sample 2 group. They have nothing in common. If that is the case, then there's a decision I need to make. The same decision we made last week about standard deviations. When you are looking at a t-test or a z-test, how do you know which one to use? Should I use z or should I use t? Gesundheit. we were very clear about the way we were able to make that decision. I had to know something to be able to use Z. If I didn't know it, I had to use T. It's the thing I had to know. Let me use Z for means. I believe this is last Wednesday. Yes, Clinton.
Is it population variance?
I need to know the variance from the population. And that was sigma, right? If I knew the variance for the whole population, then I could use Z. Otherwise, I had to use S, the sample. Now, in general, knowing sigma is rare. It is hard to know the entire population variance. On the other hand, if I don't know sigma, I can use S. And when I use S, that comes from my samples. I know those, I gathered the sample data. So that's the critical piece of information. I need to know whether or not I know population standard deviation, the population variance. So, if I know this, I'm going to be given an alpha, right? My alpha is going to be my decision rule. Or I do my Z calculated versus my Z critical, my T calculated versus my T critical. So I have a decision rule. That's going to be based off of my hypothesis. And now I say, well, which do I know? So I know which test to use. Then I'm in the same boat I was a week ago. I need to do a calculated value. Here's where the problem comes into play. I now need to think about the formula we were using for Z and T in the one sample case. So go back to the formulas we were using on Monday and on Friday. I had a Z formula for Monday. Well, from Monday, that was about proportions. Let's go back to last week. From Friday and Wednesday, we were doing means. And when I did means, I had a formula for one sample. This is a formula you need in front of you. Because if you want to do any sort of Z-test, you need to know what this formula is to go in. So you should have this on your formula sheet that goes with chapters 8 and 9. What is this formula?
X minus mean 0.
Right. This is the value for our average minus our benchmark divided by.
Sigma divided by square root of n.
Okay. And this is our standard error. Another way to think of that is it's the square root of the variance over n. See how I moved the square root from being just on the bottom to being on the top, but I squared the top to make up for it. This is for one sample. Problem. I now have two. How does this change when I have two samples? Clayton, you said I needed to know the population variance. But I got two samples. They might not be from the same population. They might be from different populations, right? That means there could be two different population variances, sigma 1 and sigma 2, for each different group, right? Well, if that's the case, my standard error is going to have to take that into account. And I'm going to have to use a different standard error. Oh my. I will have two different standard deviations, two different variances, because I have two different populations. If I'm doing two samples from the same population, maybe those numbers are the same. But I don't know that in advance. And then the top is going to be my benchmark now is the difference. So my new formula for Z looks like this. Our calculated difference minus the benchmark difference over the new standard error.
Is it a plus?
Yes, that's a plus in the middle. Because what I'm really considering is I'm considering the standard error as having factors that come from group 1 and factors that come from group 2. So I need to keep those together. Now, I must tell you, this is the problem right here. It is so incredibly rare that I know the population variances for both populations that I actually don't have an example of this in the textbook. This pissed me off to no end, by the way, because the textbook is going to lay out, hey, you're going to use the z-test first, and we don't have any examples. Because in business, it is next to impossible to know the population variance. I really can only learn stuff about my samples. This is infuriating. So I went out and dug one up. And on our Canvas page, there is a PDF of a problem I stole from online. This is an EPA problem. They go out and they look at the water, and they notice the water in two different sections of the river has different pH. The alkaline behavior, the hydroxyl content as opposed to the acidity, is known to be normally distributed with a given standard deviation. This is the thing that I would not know otherwise. I don't know where the hell they got that number from. Probably from years of testing and so on, but they give it. And then they say if you go downstream, the standard deviation is 25 milligrams per liter. So I know both standard deviations. I don't know where they got this from. But notice they did some readings in the upper level, some readings at the lower level, and now we want to compare, is the alkalinity of the water in the lower greater than the alkalinity in the upper? If I let upper be group 1 and lower be group 2, I'm asking if the average went down. So that's my null hypothesis. And then I can do exactly the test we want. Average 1, average 2, standard deviation 1, standard deviation 2. Hey, at 1%, they gave me an alpha level. So I know what alpha is. My p-value is 0.0051, which is smaller than 0.001. What do I do with my null hypothesis? Did the calculation? I now need to know what the decision is. We did all the work. What do we decide?
We reject the hypothesis, so there is a difference between.
That's exactly correct. My p-value is smaller than alpha. My critical value is 2.326. My calculated value is 2.57. My calculated value is bigger than my critical value. I'm in the rejection zone in that corner. Out we go. There is a difference in the alkaline behavior of the two rivers. Maybe there's some plant in the upper regions that is sucking up some acid, leaving a more basic solution. Maybe there's some chemical plant somewhere that's ejecting acid into the water in the lower reaches of the river. So there is a difference, and we conclude that the alkaline behavior in the upper reaches is significantly different in this case. The lower region is much bigger than the upper region. Well, it's bigger than, not much. But just looking at these two numbers, then I can ask, is this a meaningful difference? Not just statistically significant, is this a practically significant? The average in the lower river is 99, the average in the upper river is 80.5 in terms of milligrams per liter. Is that a huge difference? 19 milligrams per liter? Now we need to go talk to chemists and figure out if this means something. It's statistically significant, but I don't know enough chemistry to be able to say if it's practical. Questions? Jacob, I noticed you tapping away at your calculator furiously. What's going on?
I was putting the reasons to all this.
Well, if I have a list, then it's going to do the standard. So we're going to have to put all of these into the list, right?
Yeah.
Okay. But I can also do this calculation on here directly from the summary statistics. So if I do a 2-sample z-test, right? That's what that says right there. Instead of giving it the data in list 1 and list 2, I can give it the statistics. And then I just have to provide the standard deviations and the averages and the counts. So I was told, stat, test, 2-sample z-test. I was told for group 1 that the standard deviation, the group one is the upper and group 2 is the lower. So lower reaches of the river is 25. Upper reaches of the river is 10. We did the average for the for the lower region to be 99. There were 15 in that group. For the upper region, 80.5, and there were 10 in that group. Now that's what you would have to calculate with the stats in the lists. Now we were doing a one-tail test. 2.5737. And the p-value it's giving me is the CDF, right? Since we're doing a right tail test, I take 1 minus that number, and that's where I get 0.005 from right here. I can do this all on my technology. That's really, really important. Because the actual calculation is a pain in the ass, right? I'm going to have to do 2 averages, 2 standard deviations, and then this big calculation. Doing this on here, that's a lot faster. Realistically, I'd be better off doing it in Excel, wouldn't I? Here is a blank Excel sheet. I'm going to copy in the numbers just like you were doing. This is for the upper. The numbers are 91, 75, 91 again, 88, 94, 63, 86, 77, 71, and 69. And then for the lower, I can spell too. 86, 95, 135, 121, 68, 64. See why there's so much more variance up here? 113, 108, 79, 62, 143, 108, 121, 85, 97. With me so far? If I click on data, a lot of the data analysis stuff we did for histograms, they were all there, right? All of our descriptive statistics stuff was there too, yes? Click on that data analysis over here on the right. You are in my way. And I see a bunch of stuff here. Way at the bottom, it says z-test. 2 sample for means. 2 sample for means. That's what I want to do. Variable 1. Variable 1 is here. We did the upper as group 1. No, we did the lower as group 1. Stop. Redo that. The lower was group 1. The upper is group 2. Hang on a second. I think I missed a number. No, that's right. I think the difference is 0. I just wanted to know if one of them was bigger than the other, right? So I'm saying, hey, I think the hypothesis difference is 0. Oop, keep going. Variance number 1. We knew the variance for group 1. The variance for group 1 was 25. And the variance for group 2 is 10. Yes, I included my labels. And now I need to change alpha from 0.05 to 0.01. Please notice something big happened here. 99 and 85, 80.5, those are the same numbers we had before. Is our z-value big? Is our p-value small? Reject the null hypothesis. I'm looking at that, I'm seeing 11.3. What the hell? How'd they get 11.3? Did I must have typoed something. Let's go back and do that again. B1 to B16, 86, 95, 135, 121, 68, 64, 113, 108, 79, 62, 143, 108, 121, 85, 97. Those are right. 91, 75, 91, 88, 94, 63, 86, 77, 76. Those are right. 25 for variable 1. And 10 for variable 2. No, that's the right calculation. When you run through this on your calculator, do you get 2.57 or 11?
Yeah, I got 2 well, yeah, 2.57.
Okay, that means I don't know what the hell Excel did to give me 11 point something. I think there's a screw up somewhere. I have to go back and figure that out. But the big problem here is that this is such a rare occurrence because 99.9% of the time, I don't know the population variance. So while this is a worthwhile behavior, that's the problem, knowing sigma 1 and sigma 2. I want to do this. So I need to ask what happens in the real world. Okay. I'm going to need to use S1 and S2 instead. And if you go back and you look at the t-test simply replaces that sigma with an S, doesn't it? In the one variable, in the one sample t-test, the only thing that changes is that sigma becomes an S. But now I've got two of them. And if I'm going to use T, what else do I need?
And
Why?
what the degree of freedom?
Because I need my degrees of freedom. But I've got two groups. So how do I figure my degrees of freedom when I've got two groups?
And minus what?
But n is itself n1 and n2, right? So if I decide I'm going to use the degrees of freedom as n1 minus 1 plus n2 minus 1, which is exactly what you're telling me, then what I'm really doing is I'm basically putting them all in one pile, aren't I? I'm not kind of separating them. Because I made them one giant pile of degrees of freedom. I don't know if I'm allowed to do that. So this is an option. But in order for me to use this option, I'm really making an assumption about the population variance. Because if I'm going to put them in one big pile, what I'm really doing is saying that sigma 1 should be the same as sigma 2. Now, remember, I don't know sigma 1. I don't know sigma 2. I just don't know what these numbers are. But I'm making an assumption that they're really the same. I could do that if I knew both my samples came from the same group, right? Like I said earlier, I take 5 of you and I ask how much sleep did you get last night. I take another group of 5 and I ask how much sleep did you get last night. That comes from one big group. You should have the same variance as a group, as your son. But if I went to this class and I asked 5 of you how many hours you sleep last night, and then I went across the hall to Dr. Burns' class and I asked 5 of them how many hours they sleep last night, then I don't know that the variances are the same. So I couldn't make this assumption. If I do this, I need to average the variances. But the groups might be different sizes. In our example we were just working with, I had 10 samples from one side of the river and 15 samples from the other. So I need to kind of make a weighted average instead. That's called a pooled variance. SP. And it's really a weighted average of the variances from the other one. S1 squared, S2 squared, so SP squared. Variances. So we're going to define this. SP squared takes the first variance multiplies by the degrees of freedom from that group, takes the second variance, multiplies by the degrees of freedom from that group, and adds them together. And then divides by the total degrees of freedom that you wanted to use Alessandro, right? So I have n1 minus 1 times s1 squared. I have n2 minus 1 times s2 squared. And then I divide by n1 plus n2 minus 2. And this is what I use instead of sigma. The t value that I get is our average minus our benchmark over SP squared over N1 plus SP squared over N2. My standard error changed again, but SP has to be calculated from here. Doesn't that just suck? I'm going to do this on calculators. I'm going to do this on computers. I'm not going to do this on my own. This is referred to as a pooled or combined t-test. So those three formulas go together. If I can make the assumption that I have the same variance in the groups, then I can do this. Again, I just said a dirty word. If I can assume. I'm going to refer to that as the equal variance case. But that means there's another case. The other case means I can't put the variances together. And if I can't pool them, I'm going to have to use each one separately. So that means my formula is going to look like that. S1 squared over N1, S2 squared over N2, they're separate from one another. We don't combine them at all. But now I can't put them all in one pool. So something else has to change. And it took quite a bit of work to figure out what should change. But the other thing that should change is df. The formula sucks. Behrens and Fisher proposed this idea, and a guy by the name of Welch came up with a new formula for df. I have literally just hit the time lock on the clock. I'm going to start with that formula on next class, and then we're not ever going to do this crap by hand again. So I just wanted to show you that these formulas are not vacuous and they don't just do magic. You are reminded that chapter 9 will be due on Friday. Yeah, I will see you all then. Have a wonderful rest of your day.